hope you are having a good day. It's actually Friday for me. I'm working a little bit ahead. Um, just did a workout with my kids. If any of you have little siblings who are in elementary, you should totally check out their PE workouts. They're crazy. A lot of fun, but it was a good workout. But anyway, that's what I'm up to. And today we're going to talk about 10.3. Which is about hypothesis tests again. So 10.1, we talked about what is a hypothesis test, how do we state those hypotheses, and how do we state our conclusion. And then in our last lesson, section 2, we talked about how to do a hypothesis test for a population proportion, what proportion of the population has a certain characteristic. Today, we're going to talk about hypothesis tests for a population mean. So, what is the mean for a population based on what we know about a sample? So, as we did in the last chapter, when we worked with confidence intervals for a mean, we're going to use our t-distribution instead of the z. So when we worked with those z values, one of the things that we need to know to find a z-score is the sigma, which is the standard deviation for the population. But if you think way back to the beginning of the year when we first learned what sigma is, what a standard deviation is built from a mean. So to find a standard deviation, we take an observation and a mean, and we take the difference of all those, and then we square those differences, we add them together, we divide it by how many is in our sample, and then we take a square root. So to find a standard deviation, we have to know the mean so that we can take all those differences. So if we already knew the mean, then why would we be doing any of this inferential statistics if we already know the mean? We don't have to infer anything. So because we don't know the mean, we cannot really know the sigma. We cannot know the standard deviation for the whole population, which is a requirement for z. So instead, we use the t-distribution that we learned about back in that last chapter, which allows us to use s, the standard deviation from our sample. So I said this before, but when I took statistics, it actually didn't make that much sense to me when to do what. I didn't understand why sometimes we use z and sometimes we use t. I just didn't get the difference. So that's why I'm explaining this again, because that was a confusing point for me, and so maybe you can relate to that, and I want you hopefully to understand it better than I did when I was a student, that z can only be used if we actually know the standard deviation for the population, which is unlikely. And so really the t-distribution is a more practical distribution for that purpose. So remember that the t-distribution, some reminders, we talked about these in the last chapter, but some reminders about that t-distribution is that it's different for different degrees of freedom, and those degrees of freedom are based off of our sample size. It's one smaller than our sample size. So if we have 34 in our sample, then we have 33 degrees of freedom. It's centered at 0 and symmetric about 0, just like z is. So that's the same as z. Because it's symmetric, the area under the curve being 1, you have 1/2 above and below the mean. That's the same as z. And then as t increases or decreases without bound, we reach that asymptote out on the sides and those tails. So the tails get smaller and smaller as they go, but it never technically closes off. And then the difference between the t and the z was point number 1, that z is the same no matter how big your sample is. T changes for your sample. And point number 5 here is that the area in those tails is a little bit bigger for the t than it is for the z. But as our sample gets bigger and bigger, it actually starts to shrink down, and the t becomes more and more like the z for bigger and bigger samples. And that's by the law of large numbers. That the bigger of a sample we take, the closer we are to actually turning it into what would be the distribution for the whole population, which would be the z. So hypothesis test. to do a hypothesis test, we need a sample that was done by simple random sampling. Okay, so true random sampling should be done. And that's just a good rule of thumb for anything. We can only really trust data if it's coming from a random sample. Now in your project, a lot of you guys weren't able to really do a great random sample just with circumstances the way that they are. But in real statistics, that's something that we would be highly concerned about, is that we want our sample to be a random sample. We need the sample to have no outliers, and we need the population to be normally distributed, or we need a large sample, which in this case, large is going to be defined as 30 or more. So if the sample size is 30 or more, then it doesn't matter if the population's actually normally distributed or not, which is why for your project, you needed 30 in your sample, because then it doesn't matter if the population is actually normally distributed or not. And we need the sampled values to be independent of each other. So we need one person's response to not affect another person's response. So like in your project, if you interviewed 2 people at the same time, and the first person gave their answer, and then the second person's like, yeah, I think about the same. I think the same. Then those aren't independent of each other, right? So we need our sampled values to be independent. Just like with the proportion test that we did in the last section, we have 3 kinds of hypotheses. Our null hypothesis is always a statement of equality, that the mean is equal to something, and that's our status quo, or our assumption given past history of this study being done. And then we have our alternative hypothesis, could be that the mean is just different than it used to be, that it is less than it used to be, or that it is more than it used to be. Okay, so step 1, we have to decide which one of those hypotheses we think is going to be the outcome. That always has to be chosen before you start doing your study. Then you're going to select your significance level. How confident do we want to be about our result? So remember the significance level that you pick, which is typically going to be 0.1, 0.05, or 0.01, is the probability of making a type 1 error. And remember, the analogy of a type 1 error is sending an innocent person to jail. Okay, so the type 1 error is rejecting the null hypothesis when you really shouldn't have rejected it. Okay, so you got to decide how serious of a problem would that be, and then choose your confidence based on that. If it's like a really big deal, you'd want to go more like at the 0.01. If it's not that big of a deal, if you make a mistake, then you could say maybe 0.1. Then you're going to compute the t-statistic, and we're going to use StatCrunch to do this computation again. Then from that, we can either take the classical approach, which would be looking at one of those t-table charts and finding our critical value on there, and that's the area in those tails, either both or just left or right, depending on what our hypothesis is, and then comparing what the t-value we got is with what the critical value is. We're going to take the p-value approach instead. So we're still going to find the t-statistic. We'll use StatCrunch to find that. Then from that t-statistic, StatCrunch will calculate for us the p, which is the probability or the area in those tails, either both or one of the 2 tails. And then, so technology is going to let us find the p-value here. We're going to use technology. And then we're going to compare the p-value. If the p-value is smaller than alpha, we reject our null hypothesis. Okay, so if we decide 5%, that's our level. That's the probability that we're comfortable making a mistake is 5%, and we get a p-value that is smaller than that, 0.03. We're going to say, ooh, I guess we have to change our mind. I guess it is the alternative hypothesis. We reject the null. If 0.05 is our level and we get a p-value that's bigger than that, 0.8, we're going to say, you haven't convinced me yet. It's not a small enough probability. Because remember, that p-value is really like the probability that this result would happen if the null hypothesis is true. Okay? So the smaller the p-value, the smaller the probability that the null hypothesis is true. So then when you're going to state your conclusion, either you reject or do not reject the null hypothesis. Okay? We always talk about what the null hypothesis is. We either reject it in favor of the alternative, or we do not reject it. Okay? This procedure is robust, meaning that if it's not perfectly normal, it's not going to really affect the outcome. However, if the sample has outliers, that could be a problem, or if we have a really small sample, that could be a problem. So definitely sticking bigger than that 30 and still checking for outliers would be a good thing. So let's look at an example here. We're going to assume that the resting metabolic rate for healthy males in complete silence is 5710 kilojoules per day. So some researchers measured this on 45 healthy males who were listening to calm classical music and found their mean to be 5708 with a standard deviation of 992.05. At the alpha 05 level, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than 5710? Okay? Previous studies have shown 5710. Did a new study. Is there evidence in this study to show that it is different than it used to be? Okay, so we're going to go into StatCrunch. Ignore that data. We'll use it for a later example. I kind of prepped it here. We're going to go into t-stats because we're using that t distribution. They only took one sample, so we're going to do one sample. And what we have here is a summary. They didn't give us like, patient number 1, patient number 2, patient number 3, all the way to patient 45. They just told us the summary of the study. So we do the summary. The sample mean was 5708.07. And our sample standard deviation, 992.05, and the sample size, 45. In the last chapter, we did our confidence intervals, so you could still select that, but now we're talking about our hypothesis test. The hypothesis was that the mean was 5710, and now we are wondering if the mean is different than 5710. So on our options here for our alternative hypothesis, we're going to choose not equal. They didn't make a guess about whether it was going to be higher or lower, just will it be different? So we're choosing the not equals. And we're going to hit compute. Okay, it gives us back our sample mean again. You could like double check that you typed it in correctly, I guess. Typed it into the computer correctly, not typed it incorrectly. You don't want to type it incorrectly. And then it gives you the degrees of freedom. So remember, in a t distribution, degrees of freedom has to do with our sample size. It's one smaller than our sample. So we had 45, it's 44. In general, once you get into huge samples, that's not totally true. I mean, if you had a sample of 5,000 something, it wouldn't just be one smaller. But in general, we'll say it's about one smaller. Then it gives us our t-stat here. Okay, so remember, t's are pretty much the same idea as z, except it allows us to use s instead of sigma. So with t's and z's, we're thinking of how far is it away from the mean. So here's our mean, a t-value of negative 0.01. Well, negative means smaller, so a little bit smaller than the mean. I don't know which way this is actually going to record. I always say that. I don't know how it flips the camera or what, but a little bit smaller than the mean, but like hardly at all. That t is almost 0, which means it's pretty much right at the mean. Our p-value is huge. So remember, the p-value is kind of like a probability that the null hypothesis is true. There's like a 99% chance. So I'm going to say the null hypothesis is still true, right? So we are not going to reject it. But remember, we never actually say that we're accepting the null hypothesis, because that's the idea of, in court, we never claim somebody to be innocent. We can only claim them to be not guilty, because we don't know for sure. I mean, that's a really high percent, but we still can't know for sure. So we're just going to say we are not going to reject the null hypothesis. Okay? So in this case, very large p-value. It doesn't even really matter what our alpha is, whether we chose alpha, this said 0.5, but it really doesn't matter because 0.98, that's about as big as it can be. So we are definitely not rejecting our null hypothesis here. Okay, so this goes through that same thing, choosing what our hypotheses are going to be, that we're choosing the not equals hypothesis and our level of significance, calculating the t-stat, but we're not doing that by hand, okay? And then we're using the p-value approach, so finding the p-value, which it says is more than 0.5. Well, it is actually a lot more than 0.5, so I don't know why they just said that. But we are definitely going to fail to reject the null hypothesis. We're going to say there is insufficient evidence at the alpha 0.5 level, or really any alpha level, to conclude that the mean RMR of males differs from 5710. Okay? There's really no evidence to say that it is different. Okay, next example is pennies, no, quarters. So we looked at pennies in the last chapter, I guess, and now we're upgrading ourselves to looking at quarters here. So according to the U.S. Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different than 5.67. So the state quarters, they all have different designs on them. So presumably, one of them that has, a little bit more, a little bit extra in its design could weigh a little bit more, maybe, or weigh a little bit less, right? Because maybe it doesn't have quite as much. So the researcher is wondering, is the weight different? Okay, that's the question. Is the weight different than the standard quarter? So randomly selects 18 state quarters and obtains the following data. So I already went ahead and typed it in, and we're going to use a 5 level of significance, an 0.5 level. So stat, t-stats, one sample with data. This time we actually have the data, the weights of the 18 quarters. So we're going to go with data. We have to tell it where's our data. I put it all into var1. We're going to choose our hypothesis test. We could also choose this confidence interval, and I'll show you that in just a second. Our mean for quarters is 5.67 for standard quarters, and we're wondering if these state ones are different, are not equal to that. Okay, and you can make it do some different graphs here and stuff, but I don't really care about doing those graphs, so I think we'll just go ahead and compute. All right, so it gives us what our sample mean is. It does not give you your standard deviation. So if you need that, you got to remember back to the beginning of the year. When we went into stat, we went into summary stats for the column. So this is like way early review. We went into var, and then it has all different things selected here. And that should cover whatever we need. So it gives us here our mean and our standard deviation. So if we needed to know what the standard deviation is, what the S is, this is where we would have to get that. It doesn't give us that when we do the confidence test. So make sure that if you need that standard deviation, you come into these summary stats. So that gives us our mean and our standard deviation, median, range, quartiles, all those other things that perhaps we could be interested in knowing. So back to our hypothesis test, we got our mean here. The mean for these quarters is 5.70. So that seems different, but not super different, but it does seem different, right? Our t-stat, 2.75. So remember, that's like a comparison to the mean. So the mean, 2.75, means 2 3/4 standard deviations above the mean. So remember that 68, 95, 99.7. So this is between the 95 and the 99.7. And it turns out that that p-value then is 0.0136. So if we're choosing an alpha 0.5 level, the p-value is smaller than that. So we're going to say, I guess you proved it to me. That seems like enough evidence. I'm going to reject the null hypothesis in favor of the alternative. If the researcher had chosen the 0.1 level, now this is not enough evidence. because this is bigger than 0.1. So the level of confidence can matter here. So the researcher had chosen 0.5. This is enough evidence. Another way to think about this problem is to think about a confidence interval. So I'm just going to go back in here. And instead of choosing the hypothesis test, I'm going to choose the confidence interval. Now, because we have an 0.5 level, I'm going to leave this at a 95% confidence interval, and I'm going to compute. So here's our confidence interval, 5.68, we'll say, to 5.73. Well, 5.67 is just smaller than that lower limit, so it's outside of our confidence interval. So if we are 95% confident that the mean of these state quarters is between these numbers, well, that doesn't include the 5.67. So we're 95% sure that 5.67 cannot be right, must be different. However, if we change this to a 99% confidence interval, now 5.67 is in that interval. So the confidence level could matter here. So that's the relationship between those confidence intervals and hypothesis tests. So you can relate those two ideas and use a confidence interval to kind of back up your claim on a hypothesis test. All right. Back to this. So they started by looking at a graph to see, does it look like it is somewhat symmetric and no outliers. Remember, it's a really good thing to check for outliers, particularly in a small sample. The sample was only 18, so smaller than the 30. So we'd want to make sure that we don't have any outliers, and so that's why they did this graph. So that would have been a good thing for us to check too, and I just kind of neglected to do that. So set up your hypotheses. We are looking at a different hypothesis, so not equals, significance level. Use StatCrunch to find your t, and then with the p-value, we find the area, and it said that that p-value was 0.02, which is smaller than the 0.05, so we reject the null. However, if we had chosen alpha 01, we would not reject the null, so tricky there. So at the alpha 05 level, there is sufficient evidence. All right, now when a large sample size is used in a hypothesis test, the results could be statistically significant, even though the difference between the sample statistic and the mean and the null might have no practical significance. So when we say something is statistically significant, that means we have gained enough evidence to be able to conclude in favor of the alternative hypothesis. It doesn't mean that this actually matters. That's kind of sad, right? It'd be kind of sad to like go through doing a whole study and then come to find out like the results don't matter. But here's an example in a second of what that means. So practical significance refers to the idea that the difference actually matters, that it's enough to be concerned about. So go back to this, sorry if it's too small to read. In 2003, the average age of a mother at the first time of childbirth was 25.2. To determine if this age has increased, a random sample of 1,200 mothers, so big sample, is taken and found to have a sample mean age of 25.5 with a standard deviation of 4.8. Okay. Determine whether the mean age has increased using a significance level of alpha 05. Okay, so t-stats, one sample, summary. It did not give us all 1,200 pieces of data. Sample mean was 25.5. Sample standard deviation, 4.8. Sample size, 1,200. Hypothesis, it was 25.2, and our researcher is wondering, has it increased? Are women waiting longer before beginning a family? So we're going to go ahead and run our test. Okay. Our t-stat is 2, so remember 68, 95, 99.7. This is more than 95. That means that p-value is pretty small here, 0.01, smaller than the 0.05. If 0.05 is our level, we have enough evidence to favor the alternative hypothesis. So we would say we reject the null hypothesis at the alpha 0.05 level and conclude that the mean age of mothers at the time of the birth of their first child has increased. So now, the question is, does it really matter? So this test says that, we'll come to our conclusion. So we went through, set up our hypotheses, our significance level. We used StatCrunch to find the t-value and our p-value, and we are concluding in favor that the age is older. But does it really matter? So it used to be, the last study showed that the mean age was 25.2. Now that's because there's 12 months, not 10 months. That's not exactly. So 25.2, 0.2 of 12 is 2.4. So like 25 years and 2.5 months old, okay, the first time that they have a child. Okay, well, now this sample showed 25.5. So that's like 25 years and 6 months. So 6 minus 2.4, 3.6 months, okay, times about 30 days in a month, 108. So this study shows that women are waiting 108 more days before having a baby than they used to. 108 days, like that doesn't even matter. That's less than a third of a year, right? So the difference between statistical significance, this is statistically significant. It shows that the average age of women is more than it used to be. But does it really matter that it's more than it used to be? Because saying that it's more than it used to be kind of implies like, oh, women are waiting a lot longer to have babies, right? They're starting careers, they're doing, you could start to make other conclusions that are not necessarily true about it when you hear the statement that we have statistically significant evidence to show that women are waiting longer to have babies. Well, how much longer are they waiting? A couple months, few months. Does that really matter? That they're waiting a few months longer? Probably not. So that's the difference between practical significance and statistical significance. Sometimes the statistical significance isn't really life-altering in any way. So large samples is more likely when this is going to happen, that we're going to end up with statistically significant data, although maybe not practically significant. All right, so that's the end of section 3. In section 4, we're going to just look at a few examples of, once again, kind of like in the last chapter, how do you tell which test to do? So when you're working on 10.2 homework, you know that you're going to go and choose those proportion stats. When you're working on 10.3, you know you're going to go in and choose those t-stats. What about when you're working on the quiz? How do you know which menu to go to or what it is that you're testing? So in our 10.4 lesson, we'll take a look at a few examples and look for some keywords there. So I'll see you again soon for that lesson. Have a great day, guys. As always, ask me whatever questions you have, and I am happy to help.